And I'll go back to participants here. So remind me to take attendance later if I forget. I want to make sure I give credit where credit is due. And let's get started. So today we are going to talk about solving logarithmic equations. So on Thursday, we are going to be talking about quadratic functions. So we're going to change gears on Thursday. I'm going to go down to my desktop. If you have a question, please ask. I don't want anything to hold you back. I'm here for you. I love to see students succeed. I've been teaching a long time. This is quite different, the way we're teaching now, because it's not the same as in a classroom. In my ALEKS classroom, I usually give a mini lecture, what I call a mini lecture, and then I let students work in the lab, and I go around and help them for 30 minutes or so each class period. And that allowed me to connect with my students and really to get to see how I best could help them. And I so wish we had that ability with a remote class, but we really don't have that ability to do it that way. And so we just have to make the best of our environment now, and that we need to put our health first and so forth. So if you need any help at all, please reach out to me. I'm willing to help you. I want to see you be successful in the course. At the same time, when it comes to proctored testing, though, I have to be mindful of what truly the word proctored testing means. And that means that I know the student is who, by the student ID, I don't have the luxury, unfortunately, of knowing every one of you in the classroom. So I wish I did. But I'm willing to help you in any way I can. If the department if it's a departmental policy, I can't violate a departmental policy. And the proctoring restrictions, violations, those were given to us by the department co-chairs. So I just wanted you to know that. So let's get started. So if you have any questions, stop me. I don't want these problems we are going to do today. Some of them are a little bit on the lengthy side, and I don't want something small to keep you from surging. I mean, we all sometimes need that little somebody to tell us how to do something small, and then we can surge and do the rest of the problem. So if there's something little holding you back, please let me know. I want you to be able to do these problems. And I know you can do these problems with some help, perhaps, but you can do that. So please ask me questions. You can unmute your mic and ask me questions and say, hey, I've got a question, and we've got documents so that we can get to the particular place in the document and we're all on the same page. So I think we're good that way. So let's get started here. And let me go right here. So what I want to talk about first, and is the class recording, do we have, yes, good, is we have looked at solving exponential equations where the variable is in the exponent. Last time we looked at solving them using two different methods. The first method, like basis, equate the exponents, meaning make the exponents equal. That doesn't work much of the time. It works in under limited conditions. We have to be able to match the bases to use that method. The other method we used was take the log of both sides. This works all the time, really. Although it's more to write out than use this when you can. So I wanted to point that out, and exponential equations have a variable in the exponent. Now, logarithmic equations, the variable is not in the exponent like it is for exponential equations. The variable is actually in the argument. So every log has three pieces to it, all of which represent one real number for each different x. So a log has the log part, it has the base, it's sometimes understood like base e or base 10, and it has an argument. So the variable is going to be in the argument when we're talking about logarithmic equations. So how do we solve logarithmic equations? Again, we can do something different if we have like bases. Like bases, this time we will equate the arguments. The other option is to convert to an exponential equation. Notice for exponential equations, we are going to involve a log. Remember, for a special exponential function, for each special exponential function, there's a special log that is the inverse of it. So what we're really using is the inverse of an exponential function, which is a logarithmic function. In some sense, we're using the inverse. And down here, when we want to solve a logarithmic equation, a logarithmic function has an inverse, which is an exponential function. So that's why we're converting to an exponential equation. That's what allows us to convert to an exponential equation to solve it. So what's really important is to know where the variable is for an exponential equation. The key word here is exponent. The variable is in the exponent. For a logarithmic equation, the variable is in this argument. What are we taking the log of? That's the argument. And we will spend a lot of time talking about arguments today. There's really only two strategies when you have a solving an exponential equation or when you are solving a logarithmic equation. There are only two strategies. The first strategy in both doesn't work much of the time. So almost all the time, if you want to solve an exponential equation, you will need to at some point take the log of both sides. Almost all the time, if you want to solve a logarithmic equation, you will need to convert to an exponential equation to do so. So let's get started, and we're going to do a series of progressions here. I've had two daughters in gymnastics, so I know all about progressions. They're not doing gymnastics anymore, but they did for a while. They're doing dance now. So anyway, so let's start with this first topic here. We're going to start small and then work our way up. Solve for x. Log base 8 of x. Now, log base 8 of x represents one real number. It changes when the x changes, though, what real number it represents. So log base 8 of x equals -2. Our argument here is x. And let me get this up. Our argument here is x. It's important because all arguments must be positive. We're going to spend a lot of time talking about how to check to make sure your arguments are positive. Otherwise, you're going to need to throw something out, and that's something we will also talk about. So I just copied down this log base 8 of x equals -2. I just copied it down here. We've already practiced these conversions when we were converting from logs to exponential functions last week. I believe we did that. So it should be pretty familiar to you. So we want to convert this to an exponential equation. There's no way we can get matching bases on both sides because we only have a single logarithm in this equation. So the other strategy isn't going to work here. So we want to convert this to an exponential equation. And we did that before. We converted between exponential equations and also logarithmic equations. So you should be pretty familiar with that. So we start with the base, we then look for the exponent, and then we do what's left. And remember, a logarithm is an exponent. So we're going to start with the base. The base here is the base of the logarithm is 8. So I just wrote down 8. We then need the exponent, the entire log, all three parts, log base 8 of x is an exponent. That exponent is -2. So then we put -2 up in the exponent here, and that equals what's left. What's left is the x. So this is our equation that we need to solve. So how we do that is, I didn't try to just put 8 to the -2 in. I'm guessing Alex wouldn't take it, but they may, I don't know. But one thing you could do is flip this to the denominator. Usually in math, we write everything with positive exponents. So if you flip this 8 to the -2 to the denominator, all that changes, the only thing that's going to change is the sign right here. It's going to be the opposite sign. So this is 1 over 8 to the, not -2, but to the +2, the opposite sign, +2 in the denominator. So that's one way to do the problem. The other way to do the problem is to take 8 Mountain Peak, negative bottom row of calculator, of the graphing calculator, and then put make sure you have a -2 in the exponent, and then math enter, math bracket. And one thing is, when we are math bracketing it, we want to make 100% sure that we've right arrowed out of the exponent. And then I'm going to math bracket, math enter, and I get 1 over 64. If you get to 1 over 8 squared, you can, that's 8 times 8, which is 64. So ever how you want to get the answer here is fine. Just make sure that Alex takes it, and you'll be fine on the test. Any questions here? Feel free to ask questions. Let me just see a show of hands. You can raise your hands. How many of you feel like you've understood the first problem that we've gone over today? I am not asking for you to understand everything super perfectly, but you think you've got a pretty good handle on it. Like you're 75% certain you could get 75% of the problem correct. How many of you can, by a show of hands, think you've got a pretty good understanding of that? Keep showing your hands. I just want to see. Okay. So feel free to ask me questions at any time. I just want to get a pretty good understanding, because we are going to build on, thank you. We're going to build on this. So this is just a starting point. So let's go on. And let's take a look at our problem here. And I need to go back because I don't want to leave any stone unturned. If I took this 1 over 64, that's my x, that's our x, and I put that right here, let me go get another, good. If I put this right here in for x here, this entire argument is x. Our argument is just x. This is our x. We found it to be 1 over 64. That is right here. That 1 over 64 goes in for x. And the question is, is that entire argument, which is x, which for us is 1/64, is that positive? And the answer is yes. So that's why that's the answer. You will, in these problems, you will always need to check your x in the argument to make sure that all arguments are positive. And some of the problems are going to have more than one argument. So let's make sure we start by getting into that routine. So let's look at this particular problem. Solve for x. So this time our argument is 4x minus 2. We have log base 3. What we're taking the log of is 4x minus 2. So that's our argument. We're still asked to solve for x though. But like this 83/4 would need to be plugged in for x here, multiplied by 4 minus 2 to make sure it was still positive. So let's start with this equation, just copied it down. Now we have a single log on this side, all by itself equals a number on this side, so we can convert. We're still working on problems where we can convert easily, where we just have one log. So the conversion, we want to do base, exponent, what's left? Base is 3. Exponent, the entire logarithm is an exponent, and that number is 4. So 4 goes in the exponent. Equals, what's left? What's left is 4x minus 2. That's on the normal line of writing. So this is what we need to solve. 3 to the 4th is 4 3's multiplied together, so it's 3 times 3 times 3 times 3. So 3 times 3 is 9. The other 3 times 3 is 9. 9 times 9 is 81. Equals 4x minus 2. We want to get the x by itself, so the opposite of subtraction, adding 2 to both sides, gives us 81 plus 2, which is 83 on this side, equals 4x on this side. This is really plus 0 here. 4x plus 0 is still 4x. And to get the x by itself, we just need to move the 4 to the other side. So it's participating in multiplication. The opposite is division. Let's divide both sides by 4. And we get 4 divided by 4, which is 1 times x, which is x. And that equals 83/4. Now, that's not necessarily, we've got to make sure that is the answer that's going to work for this problem. So we need to go look at our argument. Our argument is 4x minus 2. So I took the argument, it's in parentheses right here, this argument. I took the argument and wrote it down here. Now, what are we plugging in for x? We are plugging this in for x. So it goes right there. And we get 4 times 83/4 minus 2. These 4's cancel. 4 divided by 4 is 1 times 83 is 83. So we just get 83 minus 2, which is 81. So our final answer is 81. And 81 is positive. So that entire argument is positive. So that means that our x is 83/4. So we can't take the log of negative numbers, and we can't take the log of 0. Just for fun, if I try the log of 0, the log button, I don't have my calculator up, it looks like. Let me see if I can go grab that calculator or not. There it is. Okay. So what I want us to do, let me see, get back here. Yeah, we did this problem, and that's good. I'm thinking about what I want us to do, and I definitely want us to play with the logs and the ln. So let's see what we can do in a moment. I'm not remembering what I wanted to do here, but I'm sure it'll come back to me at some point. Yeah, I think we're good here. Any questions on this particular problem? Oh, I know what I was going to do. So I want to show you how what's a good thing to do. If I take this log button here, log, it's in the fourth button up from the bottom leftmost column. If I click on that and I put 0 inside the parentheses, I get error domain. Can't take the log of 0. If I then click on it again and I put in, say, -5, negative in the bottom row, 5, I get error, non-real answers. And we're only working in the real number system. So you can use the calculator to check to see if you can take the log of 0 or the log of a negative number. If you forget, or if you forget what you can take the log of and what you can't. That's where I'm going with that. So let's talk about this problem. We are now going through a series of progressions. The only thing that's different about this problem is we have a number in front here. We've got a 4 in front here. We just had an understood 1 in front of the log in the previous examples that we looked at today. So what we want to do with that 4 is move it to the other side. We want to isolate the logarithm. So I just copied down the problem right here. We want to isolate the logarithm. So that means we want to move this 4. This 4 is participating in multiplication. The opposite is division. So let's divide both sides by 4. So this side, just copied it over, divided it by 4, equals this 12, copied it over, divided it by 4. So all we're left with here when these 4s are canceled is ln of x minus 4 equals 12 divided by 4 is 3. So just for all of us to be on the same page, remember, if you have ln, you can replace it by log base e, or if you have log base e, you can replace it by ln. Why do we want to do that here? It will help with the conversion. ln is just the same as, just to be clear, this ln, whoops. Yeah, let me just get that off of there. I think it took me to the previous page. It skips around on me. Just find my place. I'm getting ahead of myself. I think it just went down on, we did that. Okay, so I know where I am now. I want to hold my trackpad just perfectly to do that. And then we also want that ln is equal to, ln You can't really say ln doesn't, it's just letters. You know, these are just letters, really. It's not a number. It's just that I want to show you that if you want to take out this ln here, this ln can be replaced by log base e. So the reason why you would want to do that is because you know what the base is here. And when we convert, we need to know the base. Or you can just remember what the base of ln is. So we want to convert this to log. Let's convert it for this, so we're all on the same page, to this ln. Let's convert it to log base e. Looking at this. So we have log base e of x minus 4 equals 3. We have a single log. Notice we have not started working with 2 logs yet. We will do that in a little while. So we want to convert this to an exponential equation. We need a base. The base is e. We need an exponent. All 3 parts of a logarithm is an exponent, so our exponent is 3. Equals, what's left is this x minus 4. Now we want to solve for x. So all we have to do is move this minus 4, the opposite of subtraction, addition. Let's add 4 to both sides. On this side, we get e to the 3rd plus this 4. On this side, this minus 4 plus 4 is 0, plus x is x, right here. So that's what we get. Oops, sorry. I have a jacket on and I just took it off. So now we want to figure out what this is. We want to do not round any intermediate computations and round your answer to the nearest hundredth. So I'm going to take and do this computation, but before we do that, let's look at the argument. What's the argument? What's the original argument? That's what we're taking the log of, and this is x minus 4. So I wrote x minus 4 here. That's the argument. And I want to plug in x. X here is e to the 3rd plus 4. So 4x, I'm plugging that in. That means we're going to get e to the 3rd plus 4 here. Minus 4, that's in the argument, minus 4. And I want to know if this argument is positive before we proceed. I don't want to figure out what that is if I don't need to. These 4's cancel. E to the 3rd is positive. You can do it on your calculator. So e to the 3rd. E is above the ln button, so we need to do a second ln to get that e. So e second ln, and then I've got e to a box, and I could just put in cube inside that box, and I get, that's how I would figure out what e to the 3rd is. I get 20.086. It's positive. So this e to the 3rd is positive. These 4's cancel. So on this side, I just have this, we just have this left, which is positive. So the entire argument is positive. So I know for sure this is the x. At least I 99.9999% sure. Technically, we would check it all the way to see if it would give us the answer. Correct. If we really wanted to check this, we would plug it in for x up here, do this, all of this, and see if this side is equal to 12. But we're not going to do that. We're just going to look at, we just want to look at the argument in that way that we looked at it. And now I want to just figure out what this is. So I'm going to go to the calculator, find e to the third, so that's second ln, and then put 3 in the exponent, right arrow down. So you want to right arrow down out of the exponent right here, this right arrow here. And then after that, we want to do a +4. And I got 24.08. Next digit is a 5, so we have to bump that 8 to a 9. Any questions on this particular problem? Anybody have any questions before we move on to problems that have more than one logarithm, that actually have 2 logs in them? I want to make sure you all understand the problems with 1 log in them. So let's go on. So we now see our first problem with 2 logs in it. And we have a couple of properties that are very helpful so that we can get the 2 logs down to a single log, and then we can use the process that we've been using class today. So one of those properties is the product rule for logarithms, and the other one is the quotient rule for logarithms. So we can use those 2 properties. And we want to solve for x this equation right here. Log base 5 of the argument x minus 2 equals 1 minus log base 5 of the argument x minus 6. We will now need to be checking our x in 2 different arguments. And it's only if it makes both those arguments positive that it is the solution. And we could possibly get more than 1x. We'll see that down the road here today. So what we want to do is get both logs on the same side. So I'm just copying over this problem right here. Copied it over right there. You really want to get both your logs on one side and hope that you can use a property of logarithms. In this case, we're going to use the product property. So we're going to solve this equation, log base 5 of x minus 2 equals 1 minus log base 5 of the argument x minus 6. So we don't want to move this one over here because that will give us 2 logs on the same side and the number 1 and 0 on this side. And how are we going to handle that? So what we really want to do is move this one and have a 1 on a side by itself. 1 is a lonely number. So that's what we want to do. So the opposite of subtracting this log is adding that log. So we're going to add this log to both sides. What do we get on this side? We have log base 5 of x minus 2 plus, didn't write in that plus sign, but it's a plus. So we've got plus log base 5 of x minus 6 equals, these cancel. This represents minus a real number, all of this, plus a real number, all of this. Minus a number plus a number is 0, plus 1 is just 1. So now what do we have? We have the sum of this log and this log, and that's all that we have on this side. What does the sum of 2 logs tell us? We've got a sum of 2 logs here on this side. It tells us if we go this direction, we get the log of a product. That's an understood multiplication symbol in there. How do we get a single log? Well, it's the log base, whatever we're working in, log base 5 in this case, of, we take the, on this side where the sum is of the two logs, we take the argument of the first log, right, over here, times the argument of the second log, which is y. We multiply those two arguments together. What are our two arguments? One of our arguments is x minus 2. The other argument is x minus 6. And then we want each one of these arguments in parentheses. And then we have our outer parentheses indicating that all of this is the argument of the log. And that still equals 1. While we're here, let's FOIL. We've got two terms here and two terms here. Let's FOIL. X squared, right there. Outer 2 minus that, so it's plus times a negative, so it's a negative. X times 6, so it's negative 6x. Inner 2 minus 2x. Negative 6x minus 2 more x is minus 8x. Last two, we've got negative times a negative, which is a positive. 2 times 6, which is 12, equals this one. So now what we have is a single log on this side all by its lonesome, which we need, equals a number. So we can now convert it to an exponential equation. So we need a base, 5, the entire logarithm, all of this equals, and that entire logarithm is an exponent, which is 1 in this case. So it's the base 5 to the first power equals what's left, the argument, x squared minus 8x plus 12 on this side by itself. We want to now solve that quadratic equation. It's a quadratic equation. We see the highest power on this x is a 2. So we want to use our quadratic equation techniques here. And usually for a quadratic equation, it's best to get 0 on one side by itself. And then also to get making sure we have a positive leading coefficient here or understood to be there. So let's move this 5, the opposite of adding, subtracting 5, and let's do it to both sides. That will give us x squared minus 8x. 12 minus 5 is positive 7. Let's factor. Luckily, we have an understood leading coefficient of 1. So we're looking for two numbers that multiply to give us 1 times 7, which is 7, and add to give us negative 8. They would be negative 7 and negative 1. So we have x minus 7, x minus 1. And we can FOIL to check. X squared, check. Outer 2 minus 7x minus 1x, that's minus 8x, check. Last 2, minus times a minus is a plus. 1 times 7 is 7. So how do we figure these out? We set each factor equal to 0. We get x minus 1 equals 0. Just to show you. So if I set this first factor equal to 0, I get x there minus 1 equaled 0. And then that minus 1, we're going to move to the other side, but it's going to go over there and end up on the other side as x equals 1. And in the same way, the minus 7 will end up on the other side as plus 7. So those are our two possible x's. Remember, all arguments must be positive. So what are our arguments? Our arguments are x minus 2. Wrote it down here. And x minus 6. Wrote it down here. What happens if I put in 1 for x here? What happens there? We get 1 minus 2, which is negative 1. All arguments must be positive. We got a negative number. So that is not, and x cannot be 1 because it results in a non-positive argument. So we have to throw that out. If we check 7 now, so if we check 7 now, 7 minus 2 is 5. That's positive. And down here, 7 minus 6 is 1, which is positive. So this is the only answer for x right here. Any questions on that? And you will see up here, I only put in, for the box, x equals box, I put in 7 only. We're going to see some no solution problems today too. So it's very important, this idea of understanding how to check your arguments. Any questions on this particular problem? Please, it's okay for you to ask me questions. I have no problem with it at all. It's I want you all to do well in this class, and that's how you learn. So by asking questions, and it's a little more difficult now to ask questions, I suppose, but I still would love for you to ask me questions, because this is really, some students actually do better on logarithms than they're doing in the course in other places, but some students don't. So feel free to ask. Our brains are all wired differently. The interaction, I think, would be good for all of us, to be honest with you. So feel free to communicate with me or ask any questions you would like, or mention anything or ask questions about how can you be more successful in the course. So it's important. Okay. Any questions on this particular question? So let's take a look at another one of these. This is just another way for me to talk about the arguments, which I've already done. And I think it's just a more clear-cut way to look at it. It saves more time saving, more efficient. I think it's a better way of presenting what I just did. So even though I say, please ignore this page, I think we need to look at it. For one, you're going to notice the answer is no solution. For another, you're going to notice we have 2 logs in this particular equation that we need to solve. And this time we are going to use not the product property for logarithms, but the quotient property. So let's just copy the problem down. I just copied the problem down right here. We want to be able to combine our 2 logs. So that means we need to get them on both sides. Or sorry, we need to get them on the same side. It means we need to get the logs on the same side. So let's add the opposite of subtraction, addition. Let's add this log to both sides. And we get, I'm going to put the positive 1 first. If you notice in the quotient property, the one with the log with the positive sign, the understood positive sign is first. So let's write the log with the understood positive sign in front first. That would be this log, log base 4 of x minus 6, minus this log, log base 4 of x minus 3. Now this is minus the same exact logarithmic expression that we have plus of here. So that actually sums to 0, and 1 plus 0 is 1. So what we want to do now is we want to combine these two logs into a single log. We have the difference of two logs. The quotient property has the difference of two logs here. And we are going to use it in this direction. We have this, we're going to use it in this direction. Okay, that's what we want, how we want to use it. So we want to find the difference of two logs. We have to have the difference of two logs with the same base to use this, which we do. We have the difference, we have this minus this. We have the difference of two logs. They both have the same base of 4. When we have the difference of two logs, same base, we can write it as a single log using that base. So in this case, it would be log base 4, right there. Log base 4 of, what do we have in parentheses here? X. Where does the X, that would be, that X is from this log here, which has an understood plus sign in front. Which of our logs have an understood plus sign in front? This one over here, because this one has a minus sign for 1. For 2, that's just understood to be plus here. That, where the understood plus sign is, that argument goes in the numerator. That's X minus 6. And where the Y is the argument of the log that has the minus sign in front. For us, that would be this, and that argument is X minus 3, and that Y ends up in the denominator. So that X minus 3 is going to end up in the denominator. And what is that equal to? It equals 1. Just copy that down. Now we can convert to an exponential equation. Very hard to solve this doing it any other way. So we're going to use our steps. We're going to take our base, which is 4. An entire logarithm is an exponent. In this case, it's 1. So 4 raised to the first power equals what's left, which is the argument, x minus 6 divided by x minus 3. I just copied that down. This is 4 to the first, which is 4. 4 we can write as 4 divided by 1, which is still 4. And then I copied this down, x minus 6 over x minus 3. The only time you can ever cross multiply in math is if you have an equation, not an expression doesn't have an equal sign in it. You can't use this for combining expressions. You have to have a single fraction equal to a single fraction like we do to be able to cross multiply. Nothing else on this side, nothing else on this side. So in this case, we can cross multiply. This is 4 times x minus 3 in parentheses equals 1 times x minus 6. 1 times x minus 6 in parentheses, like that. So let's distribute the 4 through. And well, we will do that. If I distribute the 4 through, we get 4x right there. And then positive times negative is a negative. 4 times 3 is 12. Equals x minus 6. And we want to solve for x. So let's solve for x. And we also need to move this negative 12 to the other side. So let me go and do that. So this is plus 12 right here. I'm going to move it to the other side to get the problem to work out, right? What we do to one side, we need to do to the other. So let's take a look here. So the reason why I moved, we want to move the x to one side. We want x on one side by itself. The opposite of adding x here is subtracting x. So I subtracted x from both sides. So the x is going to end up over here. So we want to move this minus 12 over here because it's a constant. So the opposite is adding 12. So that's why I did that. So we get 4x minus x. So 4 minus 1 is 3x here. 3x there. And then minus 12 plus 12 is 0. 3x plus 0 is still 3x. Equals what we have on this side. X minus x is 0. Minus 6 plus 12 is 12 minus 6, which is positive 6. So this is actually positive here. So now what we have is 3x equals positive 6. Made a little error there. Wanted to correct my error. So now we want to get x by itself. We need to divide both. We've got a 3 up here. It's participating in multiplication. The opposite is division. Let's divide both sides by 3. That'll give us x on the left side. 6 divided by 3 is positive 2 on the right side. Any questions? So I need to make these positive 2 when we check them. So we have positive 2. And this would be positive 2. And this would be negative 1. So let's look at that. Let me write this as negative 1 so it looks better. So you can see. Okay. So what we need to do, I wrote down the original equation we were given right here. We only came up with one possible solution for x. Or one possibility for x. We need to check that possibility. If that possibility doesn't check out correctly, then we're out of possibilities. The answer will be no solution. So if I plug in this 2 here, positive 2 in for x, we get positive 2 minus 3. Positive 2 minus 3 is negative 1. We need to have all arguments be positive. They can't be 0. They can't be negative. We got a negative. Can't have that. We're out of possibilities. So the answer is no solution because we got a negative argument or we got an argument which is 0. So all arguments must be positive. The answer, no solution. And let me just write that down so you can all see it. I need to go back over here. Okay. So the answer is no solution. And Alex has a no solution option. So if I go up here, the answer, no solution. Just click on that. Any questions on this particular question that we just did? Hopefully you're understanding why it's so important to check those arguments. Let's look at another problem. It's very important that we take our time looking at some of these problems so you can sort of see what's going on here. You don't want to miss a problem in ALEKS just because you didn't realize you needed to check the arguments. And honestly, I'm not sure how much of a deal ALEKS makes out of that. And ALEKS is really remarkable software. They are a remarkable software company. ALEKS I have never known in several years of teaching with ALEKS of the software to even go down, to be honest with you. And some math software goes down. I hear it from my friends that I went to grad school with. I hear it from our department here at NWAC, and so it's just a remarkable company and software, and it is really based on today's students, I think, and so forth. They do a lot of research and they run beautiful virtual conferences, and I've learned so much. I went to a conference last Friday. They even talked about, the stress of our current situation and how to reach out to students if you think you need to, and it was really well done. But let's take a look at this problem. And ALEKS is a great software, but it doesn't really give a good overview of how all of the topics are related in a particular objective. And I created all the objectives, and I tried to pick topics that were cohesive, that I could talk about how they work together, where I could do the progressions for you all. So let's look at this one. Let's solve for x. ln x. Now, when we talk about ln, what's the base? Can anybody tell me when we talk about ln, it's log base what? What base is ln? It's log base what? Anybody want to take a stab at that? ln is log base what?
Log base 10.
So I'm glad you answered. Log base 10 would be written like this. This is shorthand for log base 10. That's shorthand for log base 10, when there's no base written in and you have log. Then that is log the 10 is understood. We use this a lot, and the 10 is understood. So we don't usually write in the 10. What's log? It's log base what? So I'm glad you brought that up because we needed to look at that too. What's ln of x? What's the base in this case? This is log. What's the mystery base in this case? This is log x, but you can also consider this to be log x, but what's the base? It is base e. It is base e. So those two bases the calculator handles very easily. They're both accessible in the very first column of the graphing calculator, and they are log, which is log base 10, is the fourth button up from the bottom in the leftmost column, and ln which is log base e, is the third button up from the bottom. So we just want to keep that in mind. Log base e of x equals ln of x. We want to use that. So I just copied this entire problem, this equation we want to solve, right down here. And I'm thinking each one of these ln really represents log base e. This one, this one, this one. And you cannot separate a log. For instance, I couldn't divide both sides by x here. You don't want to do that. A log is 3 pieces, a log, a base, and an argument. So you can't take either piece away. For instance, I can't divide both sides by log. Those are letters, and they're not variables. So we can't divide both sides by log. Can't divide both sides by base e. Can't divide both sides by x. So these are, you want to consider a log, all 3 pieces together. And if you're going to move that to the other side, you want to move all 3 pieces of that log, not just one of them. So let's take a look here. This is the original problem. We have 1 log, 2 logs, 3 logs. Luckily, we have ln of 6. That's log base e of 6. If I found ln of 6 on my calculator, I get 1.79 rounded to 2 decimal places. That's a number. And that really represents log base e of 6. So there really, you need all 3 pieces for it to represent a number. You can't take one of those pieces away. So we've got the sum of 2 logarithms on this side. We want to combine those 2 logarithms. And the question is, can we do that? So we have the sum of 2 logs on this side over here. And what we want to do is we want to go in this direction here. We want to go in this direction. To give you a visual. How do we combine 2 logs? We've got it, and we want to have the sum of 2 logs right here, not the difference, the sum. We have the sum of 2 logs here. How do we combine them? Well, I keep thinking we take the arguments. We're really combining the arguments in a special way. So let me make sure. Okay, so we take these 2 arguments. Why on earth? Yeah, let me see. I think it'll work now. Yeah, I've got my pencil. Okay. What we want to do is we want to take this argument right here. Can I get this to work? If I don't get it to work, it's okay. There we go. Y and this x. So we're multiplying these 2 arguments together. X times y ends up over here. So to write this as a single log, all we have to do is write down the single log with the correct base. And then what we do is, if we've got two logs over here, okay, if we have 2 logs over here, and we want to make sure they have the same base, and we then take their arguments and multiply, we get a single log right here, and we take these arguments and multiply them together, x times y. That's what we do. So if we want to combine these into a single log, we write down the log, including the base that we want. We're working ln of x here, which is ln of x is log base e. And you can leave it as ln of x, or ln. You can leave it as ln. You can just write this. When we go in this direction, you can write it as ln over here. And then and I should say, yeah, when we go in this direction, you want to write it as ln. Let's go down one, because we're really going down here. Write it as ln of x here. And then what do? How do we get the single log on this side? So here, we're just copying down this ln of x. Not to cause any confusion, I just want to copy this down. Here, we are looking at using this property. For the right side, we want to use this property. What do we have? On the right side, we've got the ln of 6 plus the ln of x plus 4. Now, if we look at these guys, These are the arguments. How can we write that as a single log? We write it as a single log. That would still be log ln of, because that's log base e of x. That still would be ln. And we just multiply the two arguments. In this case, it was x, this y times this x, which would give us xy, or you can think of it as x times y going in this direction. So let's think of this as 6 times x plus 4 going in this direction. So we get 6 times x plus 4 in this, inside this new argument here. Any questions on how I use the product property? So in the next step, all I did was I realized that this was 6 times x plus 4. So we have multiplication over addition. We can distribute. So let's go ahead and distribute here. 6 times x plus 6 times 4, which is 24. Now let's look at what we have. We have a single ln on this side equals a ln on this side. We have like bases because ln is log base e. This ln is log base e. We have the same bases of the e. So when we have like bases, we can equate the arguments, which means we can solve by making the arguments equal. So the arguments, so you just take argument equals argument. So argument equals argument. So this argument is x. This argument is 6x plus 24. And then we solve for x. So let's move the 6x. So let's subtract 6x from both sides. This is 1, coefficient of 1 here, minus 6 is negative 5x. And these cancel, and the 24 comes down. Now we want to get x by itself, so we need to divide both sides by negative 5. So let's do that. These can't, negative 5 divided by negative 5 is positive 1 times x is x. So these guys cancel. And we just get x on this side by itself equals positive over negative is negative 24 over 5. So let's take a look. We think let's just say x is certainly negative 24 over 5. What do we need to do? We need to check that in all the arguments that have x in them. So here's the original equation we were given. Here's ln of x. Here's our first x. We want to plug in negative 24 over 5 for that. That entire argument is negative 24 over 5. That's negative. All of our arguments must be positive. All arguments must be positive. We found one that is not positive, and we only had one possibility. We're out of possibilities, so the answer is no solution. Any questions here? I want to make sure you understand when the answer to problems is going to be no solution. Let's go on. Let's take a look at this particular problem. Let's solve for x. Log base 2 of x plus 6 minus log base 2 of 20 equals log base 2 of 13. So we have 3 logs here. So we're going to want to figure out what it is we need to do here. So I just copied the problem down here. It's up to you what you do, but I will say it's probably best to do it this way. We've got log base 2 of x plus 6 minus log base 2 of 20 equals log base 2 of 13. These are numbers. Log base 2 of 20, these are known numbers. You can think of it that way. I mean, we could figure it out on our calculators. We can, if we wanted to, but since we don't, my point is, this is the only log, this is the only variable we see in the entire equation. So I would recommend that you get you could work with it like this. I wouldn't personally want to work with it like this, but you could. I would personally add this log base 2 of 20 to both sides to move it to the other side. So we have log base 2 of x plus 6 on this side. If we do that, this is minus the same as plus, so this is 0, so we're not going to have it on this side. It's actually going over to the other side, equals this log base 2 of 20 plus this log base 2 of 13. So we now have the sum of two logs. We want to get it down to either one log in these problems, or you can have two logs, but they need to be on opposite sides. And that's when you can equate the exponents. We do not want three logs. So we want to combine these two logs. We have a sum. The product property has the sum of two logs in it, and it tells us we can combine those two logs into a single log of the product of the arguments. So in this case, we would have a log, it would be base 2, and then we'd take our arguments, which are 20 and 13, and multiply those together, 20 times 13. If we do that, we're going to copy this down. 20 times 13 is 260. We now have a single log equals a single log, and we have like bases. So we can just equate the arguments. In other words, make the arguments equal. So this is an argument of x plus 6, copied down, equals an argument of 260, just like that. And if we solve for x now, we can the opposite of adding 6, subtracting 6. So let's subtract 6 from both sides. And that will give us x equals 260 minus 6 is 254. Now we need to check that in all our arguments that have an x in them. How many arguments do we have that have an x in them? Only one, x plus 6. So that's our argument here that we need to check. So let's write down x plus 6. So we want to put this 254 in for x. And if we add 6 to that, we're going to get 260, which is positive. So this is our x. It is 254. It's fine, absolutely fine to have a positive argument. In fact, we must have a positive argument in this situation. We must always have a positive argument for a log. Any questions on this particular problem? And that brings us to the end of this presentation, but I have 3 more problems I want to take a look at. And let's take a look at those now. So I'm going to go to right here. Let's look at some application problems, 3 of them. Now, you've already seen compound interest and continuous compound interest before in this course, so I know that it's somewhat familiar for you. And that was the reason why I did it earlier, so we wouldn't have to learn so much so quickly. So let's take a look at this first problem here. Hong wants to buy a bond that will mature to $4,500 in 9 years. How much should he pay for the bond now if it earns interest at a rate of 2% per year, compounded continuously? So I will say that this is what we call financial. And if you're going on to finite math, you will definitely see they spend quite a lot of time on talking about financial math in finite math. And so it's very important that you master these topics now, because that's one of the chunks of material in finite math that students tend to have that find the most challenging. So I circled these words compounded continuously for a reason. That's how you know, and we looked at this before earlier in the course, that's how you know you're going to use this PERT formula. It's actually PE in the normal line of writing, RT in the exponent. This PERT formula is because of this key word continuously. It's because of that word continuously. So what we want to do is remember what these variables stand for. In a few minutes, we are going to talk about compound interest again, but it won't be compounded continuously. It will be compounded a finite number of times per year. And that's a different formula, although the variables have the same letters, and so they mean the same, except the other formula we are going to look at has a new variable in it called n. So keep in mind, though, if you understand what all these variables mean, you will then understand what those variables mean, with the possible exception of n, which means the number of times compounding takes place per year. So just to remind, as a reminder, A in this formula means the amount at time t. In other words, so much time has gone by. It's not the amount at the start of the problem, it's the amount after so much time goes by, or you can consider it to be the final amount. What's the goal? The P, on the other hand, in the formula, and you can see A is right here and P is here, or you can look up here, either one. The P is the amount at time 0, the amount at the start of the problem. How much was deposited into the account or borrowed at the very start? So we call it initial amount or principal amount. What's the principal? How much did you borrow? Is one situation where you could possibly use this formula. This E is just a number. It's a constant. It's called Euler's number. The R is the annual rate of interest, the yearly rate of interest, and it needs to be converted to a decimal. It's stated as a percent. It needs to be converted to a decimal. The T is the time in years. So let's go back up to our problem and read the problem. So it's this key word right here, continuous, which indicates that you're going to use this formula. This word right here means you're going to use this formula. That's how you know which formula to use. And you will need to know these formulas for test 3 and the comprehensive final. It's at continuously. That's what tells you to use this formula as opposed to the other formula we're going to look at in a little bit here. So let's read this again, and I'm going to write in the letters for our variables. Hong wants to buy a bond that will mature to $4,500. So that bond's going to take time to mature, so this $4,500 is in 9 years. So is that A or is that B? Is that A or P and Y? And so A is the amount at time T, or the final amount. So this would be will mature to 4,500. That is the final amount. It takes 9 years to do so. It's not at the start of the problem. So that's our A. How much should he pay for the bond now if it earns interest at a rate of 2% per year? So now this 2%, you can look at it 2 different ways. You can write down 2, which has a decimal point right there, and you can move that decimal point 2 places to the left, 1. And if we want to move it again, we need to, that would give us, at that point, that's 0.2, but we could move it again by putting a 0 in there. So we're going to move it once to get here, and again to get here, and that's going to be where our new decimal point is. Now there's another way where, so what needs to go in for R here is 0.02. So this, we want to put this in the formula as 0.02. The other way to do that 2% per year, is to use your calculator and write it as 2%. Sign means parts per hundredth. So we have 2 parts per 100. We can write that like this. And then we can use the calculator to do that math for us. 2 divided by 100, and we get 0.02. I find this way, I feel like I'm more accurate, to be honest with you. So I generally do it this way, 0.02. Either way, we get 0.02 if done correctly. So that's our interest rate. That is R. Sorry, those are the dogs next door. So R equals 0.02. And then I forgot to do this one. 9 years, that's the time. T equals 9. So we're ready to go here. We have our formula. I just copied down the formula here. A equals PERT, P-E, RT are up in the exponent. So do we know our A? It's $4,500. So I took out A, put in $4,500. Equals, now P is what we are trying to find, because how much should he pay for the bond now? P is the amount at time 0. So P is what we're trying to find. We are trying to find the amount now. And then E is a number to the R. which is 0.02 times t up here, which is 9. So that's what we want to solve. So we want to solve for p. The first thing I would do is just do this computation right here on the calculator. 0.02 times 9. 0.02 times 9 is 0.18. So I took this out, just replaced it by 0.18. And Alex, you want to make sure you're never rounding when you replace, though, like that. And we'll talk more about that in a bit. So at this point, I just want to move e to the 0.18 to the other side to get p by itself. E is participating in multiplication. The opposite is division. So let's divide both sides by e to the 0.18. So that would be 4,500 divided by e to the 0.18. So this is going to end up in the denominator, in participating in division on the other side. So we just get this over this equals p. If we do this computation on our calculators, we get 4,500 divided by e, that would be second ln, and in that box, that box which is an exponent, I'm going to put in 0.18. And I get this many dollars, $3,758.71, but the next digit is a 5, so I've got to bump the 1 to a 2. Any questions on this particular problem? I should point out that Alex says do not round any intermediate computations and round your answer to the nearest cent. Let's look at this one first. Let's go and look at the other type of compound interest problem. This particular topics probably some students would probably say this is the most challenging one of the day. So the variables mean exactly the same as they did in the topic that we just did, except there's one new one, n. N is the number of times interest is compounded each year. So we'll come back to that. If we read this problem, if you scan it, you will not see the word continuously at all in this problem. That's how I know to use this formula and not the one we just used. So let's read this problem and let's note our variables. So suppose that $6,000 is placed in a savings account. That means at this moment. That means today. So that is the P. That is the today's amount. It's the principal. That's the deposit. If you want to deposit some money into an account, that's what was deposited. The 6,000 was placed, aka deposited in a savings account. So that's the deposit. That is our P. So let's note this as P. That's placed in a savings account at the annual rate of 6%. So you can move the decimal point 2 places. That would be 0.06. That would be our R. Like that. compounded monthly. This new variable n that we didn't have in the last problem, that tells us how many times, that n is the number of times compounding takes place per year. You get interest on top of interest. Monthly, we've got 12 months in a year, so that n is 12. Assuming that no withdrawals are made, or no deposits for that matter, how long will it take for the account to grow to $9,636? Now that's the final amount. This A right here is the final amount. So that A, we want to label this with A. Any questions so far? So I'm going to try to do this step by step for you. So let's just put in our variables down here. I've got this right up here. So let me just do this. We start with A on the left side. A is $9,636. So I'm going to put that on this left side right here. I put that right here. Equals P. Do we have a P? And the answer is yes, we have a P. It's $6,000. So I put 6,000, started this side by writing 6,000. And then we've got parenthesis here. So I opened up a parenthesis. 1 plus our R is 0.06. So I put 0.06 right here in the appropriate spot. And then over N. N is 12. Wrote that down here. That N also appears up in this exponent again. So I put the 12 in for N in the exponent right here. And then times T. Our T. T is our unknown. So we need to solve for T. What are we going to have to use in this problem to solve for T? We have a variable in the exponent. The only way we're going to get that variable out of the exponent is to use a logarithm at some point. That's an exponential equation because it has a variable in the exponent. The only ways are to do that are to get like basis. I wouldn't even want to attempt to get like basis here. So we can equate the exponents. So we have no other alternative but to use a logarithm. But before we get there, let's try to clean this up as much as possible. And before we do that, let me just point out to you something on our calculator that really is helpful. This pi here is above the mountain peak. This pi is very helpful for one reason, and I'll explain that to you in a moment. Since that pi is above the mountain peak, you would need to use whatever you would need to use your second key, whatever color it happens to be. Second mountain peak. Why do I want to do that? If I do that on my calculator, second mountain peak, and then hit enter, I get pi. Now, pi is non-terminating, non-repeating decimal. Does not terminate, does not repeat. So on my calculator, I'm going to get a rounded version of pi. But what it will tell me is something very valuable. I get 3.14159 2654. Now, why is that important? Well, what we want to do is Alex wants everything to be exact. Do not round any intermediate computations and round your answer to the nearest hundredth at the very end is really what they want. So if we're going to do replacements by taking some numbers and combining them, we need to make sure, 100% sure, that we are not rounding. This tells me how far I can go out on my calculator before rounding takes place. That's what it tells me. So the first thing I'm going to do here is I'm going to do this. Not going to try to do too much at one time. Whoops, I circled the answer. Well, I'll just circle this as well. So I'm going to take right here and do this on my calculator. 1 plus 0.06 divided by 12. And I get 1.005. I know it's exact because there are only 3 places past the decimal. This goes on many more than 3 places past the decimal. So I know I can do that. So I took this out and replaced it by 1.005. Easier to work with. And then I'm like, well, what can I do now? Ultimately, we want to solve for t. So we want to get everything away from the t that we can. We can certainly move this 6,000. This is participating in multiplication. The opposite is division. Let's divide both sides by 6,000. So when we divide both sides by 6,000, these cancel. And then we're just copying this base to a power over here. And we've got this 9,636 over 6,000 on this side. Now let's see what happens if we, with this. I now want to look at this and see what we can do. Can we possibly replace this by something? So let's use the calculator and figure out what that's equal to. 9,636 divided by 6,000. I got 1.606, again, only going out to 3 decimal places, so I know that's exact. And on this side, all we're left with is this base to a power. Now it doesn't look too bad. We still have t up in the exponent, though, and what do? This right side is this base right here, 1.005 to the power 12t. Remember, we have a power rule for logs. If you have a log, in this case, we're working base 10. We have understood base 10. We haven't been writing it in, but it's understood to be base 10. We have log base b of a base to a power. When we have that, what can we do with that power? What we can do with that power is bring it down front. Bring it down front and then not write it down. So that power comes down front. We still write down log base b of x, though. And that's what we're going to do here. So that power gets dropped down front. So we want to do what we want to do here, this power right here. We want to drop it down front. Normal line of writing, like this. And what do we get? We get 12t, comes down front, log of 1.005. Any questions so far on this? And I just copied this down. So I'm going to go to the next page. And I just copied that down again, yet a second time, so I could show you what to do. So I wanted to do that so we could see. Now our goal is to, we have t now in the normal line of writing, and our goal is to solve for t. So we want to move this 12 to the other side. This log understood base 10 of this argument is a real number. We can move that to the other side. We just want to get t by itself. So let's divide both sides by 12. Let's start by doing that. So this is participating in multiplication, so we can divide both sides by 12. Let's do that. That 12 will end up over here in the denominator. Just copy this over. That will end up in the denominator. Then this log of 1.005 is a number. We can move that to the other side. The opposite of multiplying is dividing, so let's divide both sides by log of 1.005. It's going to end up in the denominator over here. So what do we have? The 12 divided by 12 is 1. Log of this over log of that of the same argument is also 1. 1 times 1 is 1. 1 times t is t. So we're only left with t on this side. So we want to use our calculator, but it's very important if we're going to use our calculator to figure this out, that we put this denominator in parentheses, because we have one number 12 and another number log of 1.005. Anytime you have two or more numbers represented in a numerator or denominator and you use a graphing calculator, you want to put parentheses around them. So we really need to put parentheses there. And if we do this computation, it's log, it's in the first column, fourth button up, log, and a parenthesis automatically opened up. So I have 1.606, closing parenthesis. I have to put that in myself, division sign, parenthesis. I have to open that up myself, 12. And that would be log is the fourth button up from the bottom in the first column, log 1.005, parenthesis, and another parenthesis to close off the denominator. Enter. I got 7.91. The next digit is a 5, so that one's going to need to be bumped to a 2. So the time is 7.92 years. Any questions on this particular topic? You're very likely to see one of these. I suspect you're going to see one of these for your written work problem, for one of your written work problems for test 3. Any questions on what we have done today? Let me make sure, and feel free to ask questions, and I can also stick around after this conference. I want to make sure that I am getting you all down for attendance. Anybody have any questions at all? So I'm going to let you out a few minutes early. It's 1:47, but you're welcome to stick around and ask me questions. So have a great day. If you haven't voted, I encourage you to vote only if you feel safe to do so. I'm not sure what it's like out there. I did vote by absentee ballot. I've never declared a party in my life because I change. I go from Republican to Democrat or back to Republican, or, I've changed so many times in my life. I've never actually declared a party. I have conflicting, I like certain things about each party. So that's what happens there. So I just want to let you know, only if you feel safe and you haven't voted already, you might want to consider voting. So I will see y'all on Thursday, and take care for now and stay safe. Bye for now. For those leaving, if you're sticking around, feel free to stick around. Take care.
Thank you.
You're welcome. Brian, are you good? Do you have any questions?